Hi everyone, I hope you've had your rest because we have a lot in store right now. The first keynote for today is going to be given by one of the, if not the most active person in the R Shiny community, Virla Van Lempert. She is the managing director and head of data science at Analytic Health. She also offers consultancy services through Highbright BV, where she is the director. I'll say this as a fan. I am always looking forward to your posts, Virle. And having recently tested the waters of Plumber and moving and offloading my application logic outside of Shiny, I am excited to hear your take on asynchronous programming. I am sure everyone else shares the same sentiment. The stage is yours.
Thank you very much for that lovely introduction and for your kind words. So, hello everybody. Welcome. First of all, I just want to take a very brief moment to thank the organizers of the Shiny conference. I think you did an amazing job. It's all going very smoothly, and I think the first 2 days were amazing. We're not finished yet, so bear with me. And one thing I really love is seeing everybody so active on the Slack channel and also in the comments. So keep that coming. All right, so today I'm going to talk about saying goodbye to unnecessary waiting or mastering asynchronous programming in Shiny. So a little bit of an overview of what we're going to talk about. First, a little quick introduction and an intro. Then I'm going to talk about what asynchronous programming is. Then how that happens in Shiny or how you can achieve that in Shiny. Then I'm going to compare some different methods that are available. And at the end, we have some time for questions. So a little bit about me, because you're going to be stuck with me for the next 60 minutes. So I think it would be nice if you have a little bit of background. So this is just a quick overview of me. I'm not really a fan of putting a certain label upon me, so I do many different things. I graduated as a data scientist. I am a Olympic weightlifter. I was a powerlifter. I am a Shiny, well, kind of lover, you could say. Currently, I'm managing director at Analytic Health. And we do all kinds of fun stuff there with Shiny apps. I also am a little bit into Linux and JavaScript, and I love working with Azure as well. All right, so we're all here because we're Shiny developers. We love Shiny, we love apps. And that's true, we love apps until they're bloody slow. Nobody likes waiting around for applications. You can imagine in this day and age that whenever you visit a website or an app, you expect it to load immediately, you expect it to run smoothly. And unfortunately, that not always happens. And then we don't love them anymore because it gets boring, it gets irritating, and we need to do something about that. So first, let's back that up by some facts, because we can't say we don't love slow apps. And I think everybody subjectively can say, yeah, well, that's true. But some facts. Some research suggests, you can read all the resources at the end of all the slides. They will be uploaded, so you can check them if you don't believe me. But if a site takes longer than 3 seconds to load, 53% of mobile users will abandon the site. And if a site takes more than 5 seconds to load, the abandonment rate jumps to 90%. So can you imagine that if an app takes 5, 6, 7, 8 seconds to load, that you lose 90% of kind of your audience? Or it's also shown that a 1 second delay in page load time can lead to a 7% decrease in conversions, so 7% less sales or whatever, or a 16 decrease in customer satisfaction and an 11% decrease in page views. That's massive. And now you can think like, okay, I'm just building shiny apps for internal stakeholders. They are just my colleagues. They they want to see what's in the application, so they will have the patience to sit around and wait. But I disagree, and research does it as well, because even if you have an application for, let's say, your organization, so internal one, application performance issue can cost tons of money just because there is a loss in productivity, in revenue, or there are other expenses. Also, obviously, you design dashboards for a certain audience. So whether it's colleagues, stakeholders, whether that's consumers, whether that's customers, it doesn't matter. They're all your users of the app, and your users will dislike any waiting. So last fact, 84% of customers will abandon a website or app if they experience slow load times or other performance issues, and 37% of the customers will switch to a competitor's website if they experience poor performance. So I think we can all agree here and all on the same page that nobody likes inefficient apps. We've already seen it in the last 2 days as well. There also a lot of talks have been about a focus on efficiency, on how to not load things twice, only get data when needed, etc. And I fully support that. So speed matters. All right. So now you're thinking, indeed, speed, colleagues, doesn't matter. I'm just a, I don't know, data scientist, data analyst, manager, whoever is here. I don't have to focus that much on speed. But the difference is, if you build something in Shiny, you are also a software developer. So no matter what your job title is, you are working with Shiny, you're developing apps, so you are a software developer, and that comes with certain responsibilities as well. It comes with the responsibility to know about best practices in software development, and it also comes with the responsibility to make your apps efficient and run smoothly. It's your responsibility as a software developer to make sure your audience stays engaged and that everyone who uses your application falls in love with it. So we're all software developers. And to make applications run efficiently and smoothly and whatever, there are many different techniques you can use. Some of them have been discussed on the conference, others have not. There is a lot that you can do. Think about lazy loading. It's also about caching, whatever. But one of the techniques that will kind of help speeding up your app is kind of to perform similar or multiple tasks simultaneously, so that you free up the resources and by that reduce waiting time. And that's why I want to introduce asynchronous programming, because it's a tool to accomplish that you can perform multiple tasks at the same time. And then obviously that will lead to an increase in your app efficiency. So I'm even going as far as to say, okay, it's all nice to know about asynchronous programming and it's good to have skill, but I even go as far as I think it's essential, especially if you're looking at other software platforms. Think about Vue, Node, async programming, Python even. Async programming is just there, a first-class citizen in that language. So I think it's an essential skill that you should have to take your application to the next level. Okay, so we now heard that speed is very important. I kind of backed that up by some research and some research that had been done. So I'm sure you will believe that. And I mentioned something, there is a magic thing called asynchronous programming. You might have heard of it, you might have not. So what is it exactly? First, let's go a step back and take a look at how Shiny works under the hood. So basically, we are a user, we go to a web browser, and this user interacts with your application. When they do that, so when they trigger an input or change something on the dashboard, then the web browser is going to make an HTTP request to the server. On that server, an R session is running. That R session will kind of process that request, and that R session will return something, which the web browser will then render in HTML, CSS, and JavaScript. This means that whatever the app is doing, or everything the app is doing, is running on an R session. And as you might already can kind of sense, R is kind of single-threaded by default. And I'll come back to that later, single-threaded and multi-threadedness. But R is single-threaded by default, which means that R executes one task after another. If you simply run R in your R console and you have an R session and you run code there, it goes step by step. It does not do two things at the same time. So looking at this picture, you can already get a sense of, okay, if my user is making a request and that all happens, after each other in queue, then it obviously takes some time to process whatever the user wants to do. So as I said, R can only execute one command at a time. We see that every day when we're developing with R. We're going step by step through script. So this is called synchronously, or which just basically means sequentially. So I'll use these terms a bit interchangeably. I'll use synchronously, sequentially, in a queue. It all means just after each other. Your Shiny app runs on an R process as well, which means by default, your Shiny app will also run synchronously. So how does it look? Imagine you have 4 tasks that need to be performed in your application. And these 4 tasks all take some time. It doesn't really matter in this case. If you execute all these tasks synchronously, so after each other, you can see that the total length, or the time that has passed after these 4 tasks have completed, is 17 seconds in total. So you might think, oh, well, this heavy computation that I'm doing in my app only takes 4 seconds. Yeah, that's nice, but you also have other things that need to happen in the app, and they all happen after each other, which means that users in the end have to wait a very long time. That even is true if you have multiple users in the same session. So depending on your actual setup and how you deployed the app, you can choose to allow multiple connections per session, which means that user A and user B can be on the same session at the same time. This means if the first user here launches a task that takes 5 seconds, and then at the same time, like at time 0, user 2 clicks that same button or another button too that takes 4 seconds, this task will only launch after 5 seconds. So in total, the waiting time for the second user is already 9 seconds, while he or she just requested a task that took 4. So this is just inefficient. We can do that differently. If we would do it asynchronously, which means at the same time, then we can reduce the time it takes to complete all the 4 tasks to 5 seconds, namely the longest time for an individual task. And if you have multiple users, then it doesn't actually really matter when they click buttons or when they launch computations. It will just start immediately and it will complete immediately. So in this case, the second user that now also launched a task at time 0 is just finished after 4 seconds and not after 9 seconds. So this, while it still is the case that task 2 takes 4 seconds, we're not changing anything about that. But the waiting time, this unnecessary waiting of the second user of these 5 seconds, is gone with asynchronous programming. And that's the goal. So it quite speaks for itself that users have to wait longer for results when tasks are executed synchronously. And we need asynchronous execution. And it's a good thing that we're going to talk about that today, so you can learn how to do that. But first, let's get a step back, because I talked about single-threadedness. So by default, an R process can execute only one task at a time, so it means it's single-threaded. We also have a thing called multi-threaded. And I just want to make the distinction here between asynchronous programming and multi-threadedness, because it's not the same thing. If you are launching tasks asynchronously, it doesn't mean they are necessarily launched in a multi-thread. So let's take a look at the difference. So multi-threading is basically a form of parallelism. It means that each thread runs a different task. And multiple threads, they can run simultaneously in parallel on multiple processor cores. So most of the time, multiple threads is like literally putting tasks on different cores of the machine, different sections of the machine. Asynchronous programming means that you can just continue executing the main thread while doing some other stuff, or while you're waiting for other stuff as well. So you're not blocking the main thread, but it can be in the same thread, which makes me to this kind of a professionally constructed visual. As you can see, we have single-threadedness, multi-threadedness. Async can happen in both ways. You can do async programming on a single thread. You can do async programming on a multi-thread. We're not going to focus too much on that today. We're just going to focus on the green dot, and you just know that you can do them in both cases. So when would you use asynchronous programming? Most of the time, if you have I/O bound needs, which means input-output needs. It means that you are, for example, are requesting data from a database, you are reading files, you're loading in CSV files, you're generating reports. There is data going over the line. And as soon as you do that, there is waiting time involved, and this is the perfect opportunity for async programming. You can also do it when you have CPU-bound needs. So let's say that you are constructing a machine learning model, which takes a lot of resources to actually make a prediction. Then you are most of the time looking at multi-threading, because if you have CPU-bound needs, you want to make as efficiently use of the CPU as possible. But you can, in this case, also do async programming to kind of at the same time letting these tasks run. Okay, now to the fun part. How do you do that in Shiny? Because that's what we're all here for. And luckily, our best friend R has an answer for everything. So there are actually multiple ways to add async programming to a Shiny app. And I think the first one on this list is the one that people know the most, because as soon as you search on Google for async programming, you will come to something called Future and Promises. But that's not all that there is, because there's also something called CallR, and there's something called Kovo. And they're actually, I think, in order of how well they are known. We're going to dive into all three of them today. I'll show you examples, and I will also compare them at the end. All right, this is going to be a bit technical, so bear with me. A future. What is a future? Because we're going to talk about future and promises, and it all sounds a bit abstract. Well, that's because it kind of is, because a future is an abstraction for a value that may come at some point in the future. So as the name suggests, it is kind of, you could see it even as a placeholder for something that you expect in the future to be returned. A future can be either unresolved or resolved. Unresolved means that it's not ready yet, it did not finish. Resolved means it's finished. So as soon as a future is resolved, so as soon as we know we expected something, then a calculation happened, that calculation is done, returns it kind of to that placeholder, it is resolved, then the value is available instantaneously to be used in, for example, your app, or in, for that matter, your ETL process. Future has nothing specifically to do with Shiny. You can also use the future package just in your R scripts, or for machine learning tasks, or for whatever. So futures can be resolved in different ways. There's different strategies that you can use. So a future can be resolved synchronously, which in this talk is not really interesting, because we're going to talk about asynchronous programming. But you have strategies that are called transparent and sequential, that are part of the future package, that will run synchronously in the current R session. So forget that, not that interesting for us. The interesting use case is that futures can be resolved asynchronously. And this means that we can do that in parallel. So there are multiple strategies, actually, that the future package supports. They are multi-session, multi-process, and multi-core. Just have my little notes here. Multi-session basically means is that we're kind of launching multiple sessions to resolve or execute all these tasks. Multi-core means is that we're going to do it on different cores. Unfortunately, if you're a Windows user, you can't use this. It doesn't support the multi-core option. Then you also have the other one, which was called multi-process, and that's kind of a wrapper around these two others. It just means that this multi-process is going to see on which operating system you are, and then chooses the best strategy. The important thing to know is here that no matter what strategy you choose, is just the way that you tell your machine, okay, I'm going to launch some tasks. I need you to perform some extra work here. You need to figure it out one way or another. You can do that by either spinning up multiple sessions, or you can do that by, sending it to multiple cores and resolve it there. It just means that we can do stuff at the same time. An example. So this is just an R script. This has nothing to do with the future just yet. It's just a value, let's say v, and we are doing something. We have an expression there. It prints something, hello world, how original, and a number 3.14. If we run this in our R console without future, you will see that hello world is kind of triggered immediately. So even though you didn't call v, if you call v though, it prints the number. Don't get too involved in the details and around that, but it's merely about to show you the difference, what the future actually look like, because this is what it looks like as it is a future. And there we have still this v object, but we assigned it with this special operator, this percentage thingy. And what we're doing now, as we kind of execute v, then it prints hello world and the number at the same time. So it is a different way. It only kind of grabs the result when it's actually needed. Then the other two calls at the top are just loading the library, and that is kind of planning your strategy. So this is one of the strategies that I mentioned, multi-session. So that's the future. Okay, so what has it to do with a promise? A promise is actually very similar to a future. There are similar things. But the promises package is kind of an API for Shiny that uses the future package to make asynchronous programming possible. So just like a future, a promise, and as the name suggests, it promises that something will be there in the future. More specifically, a promise is the eventual result from a specific asynchronous operation. So whenever you launch an asynchronous task, you get a promise back. So you launch a task, then it doesn't have to be finished yet. You first get a promise back of, okay, you asked me something, I promise you to give you a result at some point. Launching asynchronous tasks, we also are calling invoking. So you will see when reading about async, you will see invoking a lot. You also see handling a lot. Handling means that a promise or a future that, an object that kind of represents a future value can let you know something. So that is handling. So a promise can let you know multiple things, like did the task complete or not? Did it complete successfully? If it's successfully completed, what is the value? So I asked kind of to do something, then I get a value in return. And a promise can also let you know if it fails, what the error was. So as I said, the promises package is an API specifically for Shiny. It makes use of the future package. So that's why I mentioned them both at the same go. You can use future separately for standard R processes, but if you want to work in Shiny with async programming, you need to use the promises package, which calls the future package. And this kind of quote that I said there is actually from the developer documentation of the promises package. And that basically says, look, you don't need to expect that it's just going to take a couple of lines of code or a couple of adjustments in your app, and then the app is all of a sudden, async. Unfortunately, it's not that easy. It is technically relatively difficult, and also although the promises package is an API designed to make async programming more easy to implement, it is still a bit difficult. So you also need to be aware that if you're going to start on this, you just need to sit down and take some time for it. Once you get the hang of it, it will be much better, I promise, literally. But just be aware that it comes with some a steep learning curve. Okay, so what does that look like? The promises package works with a promise-aware pipe operator, which is also a very strangely looking thing that we normally don't see when just normally programming. These 3 dots and this percentage. So how it conceptually works is we have a future. In there goes an expensive computation. Can be a model, can be a database call, can be a call to an API, whatever. Then we have this promise-aware operator, and there we basically say, okay, here you need to handle whatever you're going to do. So that is handling the result, but that is also handling in case of an error. What actually happens is that you have code that's being run in separate processes, which allows you to do things asynchronously. So basically here you will see that the top level code is running in a process called A, and then the expensive operation or the expensive code that you want to execute is kind of running in a process B. It says child process. It depends on what your strategy is, what you kind of told the future package to do. And that runs in process B. And then process A is kind of making sure that, okay, whenever process B is finished with what it needs to do, and it gave me a result back, then I'm going to handle it further and, for example, give it to graphs or tables or wherever I want to display the result. So what does it look like in Shiny? So this is the first time we see Shiny code. That is cool. So Shiny, how does it look like? So here we actually see a very simple app. On the top, we see how it was. It's kind of the server. On the bottom, we see how it will look like with promises. And honestly, if you're looking at this, it seems like, oh, this is quite doable, right? Just need to have this weird operator, some extra, I don't know, future promise function it's called, some things I need, but this is quite doable, right? So although I may have spooked you a little bit with me saying that it's a bit difficult and that even the developers of this package say that it's not that easy, but I hope with this that you can start to see, okay, maybe it is doable. Okay, so most Shiny output, as you know, they respect a value. So render text expects some character, render table expects a data frame or data table. And what you just do, if you convert that code, you just need to give it a promise instead. And that promise looks like, in this case, future promise, which is the function from the promises package that is kind of this wrapper around future. You just wrap that expensive calculation or expensive operation in there. Then you have this pipe operator, this promise-aware pipe operator, and then that is kind of allowing you to process that data. So this is now async. So that's cool. And we can do the same thing, not only with rendering plots or rendering tables, we can also do the same thing with observers and observe events. And just like outputs, observe events and observers, they need to know when they're done running and if they're done running, because they need to log whatever happened in there. And if there's an error, they need to terminate the session. So the same principle here. On top, we have how it was without async. We just have an observe event that kind of was triggered on a button that said refresh data or something. Then we read some data in. We change it to actually this future promise call. And we wrap that data, that expensive calculation, we wrap it in there. And then we give that value back to a reactive value in this case. So this is also not too complicated. Just requires a little bit of change of thinking about how you're setting up your app, but still doable. So what Promises does, if you have two users at the same time in your app on the same session, user A hits a button for a long computation, R starts doing stuff with this Promises, with this async execution that we did set up. And when this happens, user B, who is on the same session, does not get affected by that. So user B can start another calculation, can hit another button, and it will just start executing immediately. User A still has to wait for the result, but user B doesn't get blocked by it. So we've gone from user A kind of blocking, holding everybody up, and blocking basically the thread or the process. We did go to a non-blocking operation. So Promises allows non-blocking programming in cross-section context, which means across sessions, it's non-blocking. This means that when you implement it like this, it means that your app becomes more scalable, because if you can allow more and more users on the same session, that equals scalability. But user A still has to wait, right? It's not like by default, I have to say, it's not like user A, the waiting time did decrease from 5 seconds to 4 seconds. No, the waiting time for user B did decrease from 9 seconds to 4 seconds. The code is still blocking at the inner session level. So user A it still has to wait. So it doesn't do anything, or it has little difference for the latency of a single session. So if a user is hitting your application and does this expensive calculation, it's not going to be any faster because of this. Maybe it's going to be even slightly slower because there is a bit of overhead involved with setting up this async structure. So you need to be aware of that. This is particularly useful if you have multiple users on the same session. If you have only one user on a session, this by default is not going to solve your problem. And I said by default twice, because there's actually a workaround for the Promises packages to make sure that it does not block at the inner session level. I have included a URL later on where you can check that out. So what to do? What if user A, kind of what we want this non-blocking intersession behavior as well. So let's say that we're user A, and yeah, we did request that long computation. Yeah, it still takes 4 seconds. What if we want to do other things while we are waiting for the results? So what if we want to click other buttons, what we want view other graphs, do other things? So basically still making it non-blocking for current and concurrent users. Then we have something where call R can be very useful. And call R, the idea behind it is very simple. This is from the documentation. Sometimes it's just useful if you can call a new R process or separate R process without affecting the current R process at all. And that's what the package does. Sounds simple. Execution might be a bit more complicated, but the idea is simple. We just have a R session. An R session can do only one thing at a time. So why do we not call different sessions, other sessions, background sessions that help us to do things at the same time, only in a different session? So with caller, you can do a lot of things. You can just go over it, but we can call an R function. We can copy objects to a subprocess. We can invoke one-off or persistent R subprocesses. And the last point on here is actually most relevant, because we can call R functions, R CMD commands, or scripts synchronously or asynchronously in the background. And this asynchronous part is obviously what we're here for, because that's what we want. So what does that look like? We have Shiny that's running on your current R process. If we get Caller in the mix, then we kind of launch a separate R process, which is a background process. And this background process is going to do the work and then send the data back to the current R process to be displayed. And you can go nuts here. I have here one background process, but you can also have 6 or 10 or whatever you need for your application to run efficiently. So the nice thing is, as I said, it keeps the session alive, also for the current user. So it works, while Promises by design was more about we have multiple users on the same session. How can we make sure that they're not blocking each other? This is more a solution that would be very suitable for current users. So that user A is not blocked. User A can still do other things while the user is waiting. So this is kind of how you avoid unnecessary waiting. And that is what this talk is about. It's avoiding unnecessary waiting. All these solutions that I'm mentioning to you is not going to make your calculations faster. You need to achieve that in other ways. You need to do that by lazy data loading, by caching, by making data more efficient, whatsoever. This is about avoiding unnecessary waiting, because it's really unnecessary that user B has to wait for user A to complete something. But back to Caller. So the beauty of it is that it keeps the session alive for current and non-current users and concurrent users. So, and when you launch a background process, it runs whenever the user uses the app, but it even continues if it closes the app down. Because the beauty of it, these are kind of independent processes. You just launch an R process, and that will do its thing until it doesn't necessarily have to return something. So let's say you have a background process that, or you have an app that inputs some data, and that data is going to be processed and sent to the database. Yeah. That processing takes a very long time because it's you're doing all kinds of magic there. So you're sending that in the app to a background process. So then the user kind of did its job. It did upload the file, and it's like, okay, I did upload it. It said success. I'm going to close the app down. The other R session will still keep running. So if that R session does whatever it needs to do, sending data to the database, it's not going to stop that immediately. Again, disclaimer here, depends a bit on your setup, but this is what is possible. So that's a very interesting use case. Other interesting use cases is that on loading, and that's what we are using, on loading your application at startup, if you have a lot of data that you need to pull in, you can just at startup launch, let's say, multiple background processes, like 6, 7, 8, that all separately retrieve data from databases, from different tables. They all do that simultaneously. You retrieve the results, and then based on those results that you may be putting in reactive or something, you display it in the app. So this is interesting, because if you needed to do that synchronously, and you had, like, I don't know, 6 tables that you needed to query for like 2 seconds, it takes 12 seconds to load your app. If you have, theoretically speaking, all these 2 seconds in 6 different background processes, it only takes 2 seconds instead of the 12. There is a little bit of overhead, but this is actually quite doable. Other interesting use cases involve knitting Markdown documents in the background. They can take a very long time, especially if you have a PDF that needs to be involved. It can take forever. You don't want your user to wait around for that. You can just put a message there and say, "Yo, your report will be finished in 30 seconds or something." It will appear automatically in your download folder or something like that. But in the meantime, the user can still do whatever they want in the app. Other use cases, yeah, lengthy models, calculations, machine learning stuff. So what does that look like? Just don't freak out if you're seeing this. I have a gist in the resources as well, where you can basically run the app in full. So this is just a part of the app. This is basically how Caller works. So what we do is if we hit a button that says start job or calculate this or run that, then we are going to launch a background process with this function that we see that is called r_bg. So our background process. What this function kind of takes is another function that contains this expensive calculation in this example, the very heavy tasks of sleeping for 10 seconds. Then it does something, it loads the iris dataset and it kind of filters it by an argument that you can pass to this function. And once it's returned, it will do something. So this is kind of the observe event that is around it. Then there's a second part that you would need to have to make this work, because this is just calling the background process. The background process gets initiated, but you also need to check when it's finished. And if it's finished, you need to give the output back to your application. So that's this second part. And in this second part, we are going to kind of see whether the process was finished or not. And in this case, we do that every 1,000 milliseconds. This is a choice, by the way. You don't have to do that. But it is nice to, if you want to, for example, update your UI in the meantime, or whatever you want to do. In this case, I just wanted to print something so that you can see that this actually can check at a regular interval. So then we have these properties that we can access from this background process. For example, is alive, where we just literally check, okay, is the background process still busy? Because if the background process is finished, that's also a choice you can make in CalR. You can either have a persistent background process or a one-off. In this case, we've chosen a one-off. So it is alive or it is not alive. So we kind of want to see, is it kind of finished? And if it's finished, then I print something. Then I also render then the table with the results. And I simply can retrieve the results from that object as well. I would definitely encourage you to just pull this from the gist and just run it yourself and play around with it. It's a very small app with only these two functions in it. But then you can really see how it works, and then you can adjust it how you want to. Last one on the list of comparisons. We need to go a bit quickly over that given the time, but there's a lot to learn in async. So we had talked about future promises. I talked about CalR, and we also have something called CoRo. CoRo is not exactly coroutines. It stands for, it's not exactly something new. It's actually very old, from the 1960s. It is, for example, natively supported in Python. So it's not something new, but you can also do it in R with a package called CoRo. And this whole concept also involves about, okay, suspension points, suspendable functions, continuations. I'm not going to go too deep into that, because then we would be here tomorrow still. But that is a package that also allows you to program asynchronously, because it has multiple functionalities. And the first one is very interesting, these async await functions. Now, if you're a JavaScript developer, this does seem, or Python for that matter, async await does sound very familiar. This is like indeed the first class citizens of many languages. It's just in every software you will see async await, which just means I'm going to launch an asynchronous job here, and I want to await the result. And CoRo makes that possible in R as well. So CoRo is compatible with promises and also with the future packages. So why do you need it, would you then think? Because it kind of works with both of them. It also uses them under the hood. CoRo is basically just a way to do it with a different syntax. It provides kind of the same functionality, but it says, well, wait, we can do this a bit smarter, because in programming land, they do it with things called async and await. So we need to kind of copy that, and that's why CoRo came into existence. Very quickly, what that then looks like, we have an await function that kind of uses a promise. So this still works with promises, as I said. And and then at the end you will have an await function that kind of returns the results when it's finished. So let's put them next to each other to kind of get an overview. This is very subjective. I'm already telling you. It's a little bit of facts, a little bit of opinion, but all these packages that I mentioned, yes, you can launch tasks asynchronously. They all have ways to handle errors, handle results, to keep you updated, so they can invoke, they can handle. The Promises packages relies on future, call R relies on process X to launch kind of these R processes, and Coro relies on promises and future. Can it keep your app alive for the current user? By default, promises cannot, but there is a workaround, which is here in the link that you can find in the slides. Call R, yes, they can keep the app alive for the current user, and Coro, I don't think it can. Can it keep the app alive for concurrent users? Yes, they all can. Can they improve scalability? Yes, they sure can. Syntax, this is the opinion part. I would say promises is rather complex. I like Caller in that respect more, and I would call it medium complex. And Coro, I would also call medium complex because they did an effort, and especially if you have a bit of a JavaScript background, it will all seem very familiar to you. The documentation for promises is very good, while it then kind of degrades to medium and very limited. Coro, there's just not much written about it. Call R is medium. I love seeing that people start using it more. So I hope definitely this will improve in the future. Okay, so basically, with all packages, you can achieve what we're here for, reducing unnecessary waiting time by using async programming. What you want to use depends a bit on your use case, but also on your personal preference. But no matter what you're going to choose, it requires a bit of a mind shift because async programming also comes with a bit of a different way of thinking. Good. My personal opinion, as I already kind of, I think people might have noticed, I personally like really Call R. It's simple, in my opinion. You just, have your R process, then you want to do some stuff that's kind of blocking your current R processes, and you send it to another background process. The concept is simple. In the meantime, your main R session is free to do whatever it wants. And I just love that. Little disclaimer, we talked about that before. Async programming is a bit complex. It comes with a little bit of overhead as well. And because you're doing things asynchronously, you also need to expect that stuff may arrive at times you don't expect them to arrive, or arrive in a different order, because that's basically what async is about. It's launching tasks simultaneously, and it doesn't necessarily tell you, okay, this is going to be returned first, second, etc. So you need to be very aware of that when you are programming async. Good. I think I'll leave the recap. It's basically, you can read that back. But yeah, I think we can say goodbye, to unnecessary waiting due to waiting for a queue that there doesn't need to be. All right. Question time.
This was an incredible presentation, Vela. I think this is amazing. The chat is overflowing with questions right now. So I want to get everyone in the chat, as well as use that people can actually ask questions from Vela in the Epsilon's ShinyConf chat, Ask the Speaker channel. We will also try to answer as many as we can right now. If we do not answer your question, feel free to just send a message there. So the first question is from Maya from the chat. So she says, from teaching and experience, I've come to find that the biggest carries in web dev for our users is starting to think about when functions run, since we're so used to reading the scripts top to bottom. So what are your thoughts for this? Any advice on how to get, behind that mental model, or how to avoid that?
Yeah, so one thing, if you're teaching that, because indeed, Shiny app is a bit of a black box as to when stuff happens. One thing I personally very like, which is very simple, put just print statements in observers. You will see on the console immediately when stuff runs. This is just basically the main simple way. The other way, if you have a decently sized application, which means relatively small, you can use a thing called React Log, which basically helps you to track reactivity across your application. So it basically is a visual of when things actually start to execute, which will help people understand when things execute and also how long it takes. So what might eventually be blocking.
Thank you so much for that answer. Moving on, we have a question from Luis. To use the future/promise approach, are more than one core or virtual CPU necessary? As in, one calculation happens in one virtual CPU while the main one is made available, or even one is sufficient and the calculations can be divided. So, do we need more CPUs, or can it be done in one? I think that is the crux of the question.
I think this also touches a bit up on the single-threaded versus multi-threaded. It is depending on what you're choosing as your strategy. If you're using multiple threads, then stuff is being executed on multiple cores or whatever different parts of the machine. And you can launch multiple computations to, or actually the future package will do that for you. It will choose where to which core kind of to send these chunks. So it's possible in both ways. You can do it either on a single thread, so then it's using the same part of your computer, or you can do it on a multi-thread. That depends on also your operating system. And as I said, Windows doesn't support that, for example. But luckily, most of the applications that you deployed will run on some kind of Unix-like system. So that should be possible.
Awesome. I think Lewis has already commented that the question, I think we've captured the crux of it. Moving to a question from Javier. Any warnings/words of wisdom out there related to the async Shiny apps that might have concurrent users writing to reactive values containers and exporting them to a cloud environment like AWS S3 triggered from an observe event? So he says granted polling helps ensure the user is always looking for the most updated data points, but would there be any what do you think, are there any advice and ideas that about this that you have?
I think this is mainly a scoping question, right? So if you have multiple users on a session, then you need to ask yourself the question, which values, which objects are available to, within the session, or for only a connection, so a different user. And I think if you're talking about reactives that are being updated into observes and stuff, it really depends on how you scoped it. Normally, reactives that you're scoping within observe events are not accessible by other users on the same session. If you're using things like global variables or whatsoever, then they are. So it really depends on the scoping rules. There's also a really nice article that I think Posit has on the website where it actually visualizes the scoping and what that looks like and where objects are available to whom.
Awesome. And there's now a straightforward question. How many users per day or hour would you recommend to start these processes? Like, what would be the estimated, count of users or concurrent users where we should start looking into futures and promises? Now that I've said straightforward, I'm thinking it's not that straightforward and depends on the use case, but then I will let you answer that.
Well, I think the answer is pretty straightforward because I am going as far as to say already with one user, it would be beneficial in some cases if you're talking about Caller then. Because actually, it doesn't matter how big your app is or how many people you are serving. You are serving your users, whether that is one, whether that is 100 or 1,000. And you have the obligation to your users to make them happy with the app they're using. So even though you have just a couple or a handful of users that use the app, you need to make sure that this unnecessary waiting due to blocking behavior is eliminated. So yeah, I would go for whatever amount of users.
So start as soon as you can, even if it's one user and they have a lot to gain from if we use this. So I think that's a good answer. Thank you so much.
Yeah.
We have one more question from Caitlin. How do you verify or test that promises actually work, since the effectiveness is observable only on the user's side?
How would you test? You expect, even working with promises, a certain outcome. You expect your graphs to look in the same way. You expect your app to function in the same way. So you can test that how you would normally test that with packages like Shiny Test 2 or with other kinds of tests with just visual inspecting tests. So I don't necessarily think this is different. Obviously, when you are thinking about it, if you are in a background process, so if you are using CallR and you're calling a background process, it's not like you can go into that session and see what the background process looks like, what objects are available there. It's also not that if you say to call a background process is print, that it actually doesn't print anything because it's printing in the background process. It's not printing in your current session. This makes debugging a little bit trickier. But CallR also has some mechanisms to kind of feed you back whatever is being said in that specific session on your current session. It has some good documentation on that, but you need to be aware of that. It's a separate thing. It's not like you can go there.
Yeah, and since you mentioned CallR, we have a question from Olga, who says that I remember the inter-session asynchronicity wasn't allowed in the promises package by design. Are there the same pitfalls of inter-session asynchronicity in CallR?
Yeah, so I think by design, why it was not in promises, and that becomes a bit technical, was about this whole flush cycle and Shiny. The fact that by design Shiny has this flush cycle and it can only do 4 activities. One of the 4 activities, which is something like receiving, updating, it can only do 1 at a time. So that's why by design, to kind of honor that, promises did not incorporate that. You can get around that by using reactive values and stuff. But I think that especially when using background processes in CallR, it's a whole different, conceptually, I think it's different, because what you're literally saying, okay, I have a current R session, but now I have some work, spin up a new R session somewhere on the computer, do the work there, collect the results and give them back to me. So I think with CallR, you have less dependency on this whole, there's no need to keep busy with this flush cycle and everything. And also there are ways to indeed get around that with promises, with this whole limitation, because it's not even that hard. You need to do something with reactive values and set it to initialize to null to make that happen. But I can share more about that in the Slack app as well, because there's still an open issue from 2018 in that repo actually that talks about it. But it's great read.
And we have a question from FM who says POSIT Connect has the off-host execution beta. How does this tie in with the async programming?
I actually don't know that.
All right.
I don't know what that part of POSIT. Sorry.
And I think we can probably take just one more question if you're okay with that. Yeah. From Luis, we have regarding multiple users. If 3 users are triggering their own queries to a database or some long-running calculation from Shiny, does that mean 3 separate background processes will run?
Depending on how you set it up, yes. Because every time you call that function CallR background, it launches a separate function, separate background processes, and it only kills it when it's kind of finished. So in theory, yes. So you need to be aware, because if you indeed have thousands of users, then thousands of background processes are going to run. That's going to be maybe a bit an issue.
Yeah, so I think this would be more of a concern, less of from the promises side, and the future side would actually be a concern of how you actually write the overall app and how it would function. So I think that's
and
what
even with CallR, there is some pooling or polling. I must say, you can create a poll of these background processes. So there are also ways to manage it. So I just remember that I was saying, like, if you have 1,000 users, then 1,000 background processes are spun up. But obviously, CallR has some solutions for that to prevent that scenario, because it will blow up your server probably.
Awesome. I think that's all the questions we have. If you have any more questions for Virla, feel free to send her a message. And thank you so much for this extremely well done presentation. It was amazing. The comment section, I have not seen it so active since the last 2 days. So I think That's the kudos to you. Thank you again for this time.
Thank you. I hope everything was clear, and yeah, happy to connect anytime.
All right.